Okay, so fundamentals of electromagnetism. So all rotating electrical machines, including and the transformers as well, use magnetic material for shaping and directing the magnetic fields, which act as a medium for transferring and converting the energy. So under rotating electric machinery, it comes the DC machines, both DC generator and DC motor, and AC machines, which includes induction machines and synchronous machines. Transformers are non-rotating but are used as a machine in electrical systems. Now the magnetic fields are produced by two ways. One is it comes from a permanent magnet. Second, it comes from an electric current flowing through an electric conductor. So what electric current is, you can say that it is moving electric charge. So magnetic field is produced by two ways, from a permanent magnet and from an electric current. Now when the magnetic field is produced by an electric current, it is called an electromagnet. An electromagnet, and you can see, since the production of the magnetic field depends on the flow of the electric current, so in case of an electromagnet, the strength of the electromagnet depends on the current flowing through it. But in case of a permanent magnet, the strength of the permanent magnet depends on the material used for making that magnet. So we're looking at magnetic field. So now we have an electromagnet. That's what mainly we will be concentrating on, where magnetic field is produced by a flow of the current. Let's say here you have a conductor. And this is a copper conductor, let's say, made from any conducting material, and assume that there is a flow of current through this conductor, and that flow of current has a direction from right to left. So that's the flow of the direction of the flow of the current. Now what we said is, if there is an electric current flowing here, there is a magnetic field. There will be a magnetic field. Now according to which direction the magnetic field will be here, in this case, use your right hand and your thumb points in the direction of the current, then your fingers will curl around this conductor and they will give you the direction of the magnetic field. So this is how the direction of the magnetic field will be. Now this is the case when you have current flowing through a simple conductor, and that's the direction of the magnetic field. Your fingers curl in, and you can say that this magnetic field, so here I'm gonna say that's the magnetic field, and we can also call this magnetic field as magnetic flux. Flux. And in this case, it is around a current carrying conductor. So here is the magnetic field or the magnetic flux around a current carrying conductor. And let's say I want to present a magnet on these magnetic field lines. So I can say here is my magnet, and how the north and the south poles are on that magnet. So it leaves the north pole and it enters the south pole. Okay, let's use the black for writing the south pole. Okay, so lines, magnetic field lines, enter into the south pole and leaves the north pole of a magnet. So that's the case of a current carrying conductor. Now let's see, instead of a a conductor only, there are many terms of this conductor used, which is called a coil. Okay, so now we're looking at magnetic field in a coil. So let's say this is how the coil is wound. Yeah, so this is fine. Let's say this is how the coil is wound. So let's say this coil has 1, 2, 3, 4 number of turns. And there is a flow of the current, and just for showing that there is a flow of the current, we have used a battery. If this coil is supplied from the battery, there will be a flow of current. How will it will be? It will be leaving the positive side of the battery, and it will be entering the negative side of the battery. So this will be the direction of the current. So that is how it will be. Now, in case of a coil, if you want to see the magnetic field in a coil, so far we have only said there is a flow of current through this coil, and the direction of the current we have shown. Okay, now in case of a coil, you use the same right hand, you curl your fingers in the direction of the current, and your thumb points in the direction of the magnetic field. So when you curl your fingers in the direction of these blue arrows, you will see that your thumb will be pointing towards left. So that means the direction, the lines of the magnetic field will look like this. The lines of the magnetic field will be, let's say it will be going out from here and coming in here. Another one, and that is how it keep going. Okay, so these are called magnetic lines, lines of magnetic field, and this is the direction, right? That's what we said. So this is where it's coming out. That's what our thumb is pointing, and this is where it is coming into the magnet. So this is the direction of the magnetic field. And again, you may opt to draw a small magnet in here anywhere, and you can say it leaves the north pole and it enters the south pole of the magnet. All right, so again, you can say that here is the flux phi, here is the flux phi, and so on. So that's the magnetic field in a coil. We can also look at how it is in case of a magnet. So here we have a magnet, let's assume. And in case of a magnet, this is what you have. Now in magnet, we don't need to have any current supplied. So this magnetic material will have the magnetic field around this magnet. So leaves the north side and enters the south side. So this is how the direction of the magnetic field lines will be. Okay, so leaves the north side, enters the south side. And inside of the magnet, so that's the direction of the magnetic field inside of the magnet. So again, this is your magnetic field, and you can say this is the magnetic field in a magnet. All right, so the magnetic field or the flux mentioned in here as phi, the units for this flux is Webers. So this flux is measured in Webers and is a scalar quantity. And we use it W and a B. Webers is the unit for the magnetic flux. Okay, so another, you can say it is also magnetic field quantity, and it is used to express the magnetic field in the same way the magnetic flux is used. It's called magnetic flux density. So magnetic flux density is a vector instead of a phi only. So let's say we write it here, and it's represented by B, and it is a vector quantity. So it has the amount, and it also has the direction. So here in all the three cases, the direction of the magnetic field, let's say if I want to label the direction in here, so I can say this is B. Similarly, in this case, this is, I'm gonna say is my B, and in this case as well. So that's the direction. So this is called magnetic flux density. Magnetic flux density. So B is the vector quantity, and it is the strength of the magnetic field. Okay, it is the strength of the magnetic field. B, it is a vector quantity. It's called magnetic flux density and is measured in, since it's the strength of the magnetic field, so we measure it in Webers. That means the magnetic flux per unit area. So Weber per meter square, or its units are also Tesla. So Tesla is after the name of the scientist who did the research in this area. So Weber per meter square is the unit coming from its definition, and Tesla is the unit after the name of the scientist. Now let's take an example just to understand the direction of the magnetic field and the related to the direction of the current, which is causing that magnetic field. Let's assume that you have a coil which is wound around the periphery of a clock. If current flows clockwise, what is the direction of the magnetic field's density B in the center of the clock face, okay? In the center of the clock face. So you're going to use your right hand, and this is a coil, so that's why your fingers must curl in the direction of the current, which is clockwise. And you will see, if you will curl your fingers in clockwise direction, your thumb will point into the clock face. So that's an example which relates the direction of the magnetic field to the current which has produced it. Okay, another magnetic field quantity we have is called magnetic field intensity. And is represented by H. And that is also a vector quantity. Okay. And we can also make use of this quantity, and there's a law, Ampere's law. Ampere's law, which is used to solve magnetic systems. Now, magnetic field intensity H and the Ampere's law. So magnetic fields that are produced by the current flowing in the coils, and the magnetic field intensity H that is determined by the currents and the configuration of the coils. So the flux density B depends on H and the properties of the material filling the space around the coil. And how the two are related, so B equals to mu times H. This is called mu. So both of them are vector quantity, B and H. So you can see that the B has the units of Weber per meter square, or Tesla. And H has the units of amperes per meter, or ampere turns per meter as well. So H is the magnetic field intensity. It's produced by the current flowing through a coil having certain number of turns. So you can have its units as amperes per meter, or you can say if it has turns, then you can say ampere turns per meter. But this turns does not mean anything other than that it adds up to the amount of the magnetic field. Okay, so mu is the property of the material. In which the magnetic field is there. magnetic field is present. And its name is mu though, but it's called permeability. Permeability of the material, of the magnetic material. Mu. Okay. Now, mu is made up from two parts, mu 0 multiplied by mu r. Mu 0 is the permeability of the free space. Free space, vacuum, non-ferromagnetic materials. And has a constant value. So mu 0 is given by 4 pi times 10 to the power negative 7. All right. Since mu is given by mu 0 times mu r, so let's say you're talking about the material being the non-ferromagnetic material, then your mu is going to be equals to mu 0 itself. That's it. And mu r, depending upon if it's a ferromagnetic material, so in case of ferromagnetic material, you have mu r as the relative permeability. Relative permeability. And mu r greater than or equals to 1. It is 1 in case of free space or in case of non-ferromagnetic materials. But for ferromagnetic materials, its value is large. For ferromagnetic materials, its value ranges from 2,000 to 6,000. So a large relative permeability means a small current can produce large flux density. Large flux density. So we looked at 3 factors to define the magnetic field: flux, number of magnetic field lines, magnetic field density, how strong the magnetic field is, magnetic field intensity, which considers the ability of the material to impact the magnetic field as well. And mu is what relates B and H, and mu equals to mu 0 mu r. Mu 0 is the permeability of the free space or the non-ferromagnetic materials, and mu r's value is greater than or equals to 1 being the relative permeability, and equals to 1 in case of non-ferromagnetic material, and its value lies between 2,000 to 6,000 for ferromagnetic material. And the larger the value of the mu r is, means a small current can produce large flux density or large or stronger magnetic. Okay, so we're looking at Ampere's law. It's also called Ampere's circuital law. So this is the line integral of the magnetic field intensity H around a closed path is equal to the algebraic sum of the currents flowing through the area enclosed by the path. So in order to write it in mathematical form, it is the line integral of H. So H dot dl equals to the algebraic sum of the currents flowing through the area enclosed by the path. So sum of all the currents. Let's consider the magnetic field around a long straight wire. So consider here is the wire. Okay. And this wire is carrying current out of the page. Let's assume that it is, now this is a conductor only. It is carrying a current out of the page. When it carries the current out of the page, the direction of the magnetic field will be counterclockwise around this wire. So if I draw a big circle that will represent the direction of the magnetic field. So at different times, I can say here, this is the counterclockwise direction of H or B. This is how the direction of the magnetic field is. So I can say this is H, this is H, and this is H, and this is H. So the center is, this is the wire carrying current out of the page. That is how we got the counterclockwise direction for the magnetic field. And assuming that the material surrounding the wire has a permeability mu, so we're assuming it's some ferromagnetic material which is surrounding the wire, and let's assume that this is radius or distance r. Now we can say, using Ampere's law, H dot dl line integral equals to mu I. So in this case we can say H, and the total length assume is L, okay, equals to, let's say this is the total current carried by the wire, in this case as I, okay, that is the current carried by this wire. Now, since this is a circle, so everybody knows that the length is given by the circumference of the circle, which is 2 pi r. So we can say H times 2 pi r equals to I. And we can say H equals to I divided by 2 pi r. And we can also say B equals to mu times H, so which will be equals to mu times I divided by 2 pi r. So that's the Ampere's law applied to a wire carrying a current. Okay, so B equals to mu I over 2 pi r, where r is the radius of the circle, which is made by the magnetic field lines. Now that was the case of a wire carrying current, a simple wire carrying current. Now let's assume the case of a coil. Coil. Okay, so let's say here we have a coil. Which is wound around this core. Okay, that's a core, and this is where the coil is. And it's around the whole periphery of the core and assumed to be same everywhere. And there is a flow of the current through this coil, so I'm going to connect a battery or a source. And let's say this is how the source is connected, and if that's the case, this will be the direction of the current I. And if that will be the direction of the current, this is how it will be. Now this is a coil, and if this is the direction, okay, and there we go. And if that's the direction of the current, so in case of a coil, your fingers curl in the direction of the current, and your thumb gives you the direction of the magnetic field. So if you curl your fingers in the direction of these blue arrows, your thumb is pointing in clockwise direction. So the magnetic field will look like this. If you consider every conductor and if you consider all of them, so this will be the direction of the magnetic field produced by the current flowing through this coil, the blue coil. Right, so red shows the path of the magnetic field, only one line, although you're gonna see more, and the arrows shows the direction of the magnetic field. So this is your B, or you can say this is your H as well, does not matter. B and H are related through mu. And let's assume that we have drawn this magnetic field at a mean radius of r value. So at a mean radius of r value. And let's also assume that this blue coil has n number of turns. N number of turns. Now if we apply the Ampere's law, in this case it will be again, so H dot dl equals to sum of all the currents, I or I. So dl is the increment of the length along a closed path that encloses the current, and H is the magnetic field intensity at a particular point of the space in amperes per meter. And we also know that since this is a circle, so it's going to be H times L is the total length, and the total current in this case is I. That's where this has come from. For one conductor, let's say, right? For this one, it's I flowing. Since there are n of them, so we're gonna have n times I as the total current. So it's gonna be I1 plus I2 plus I3 n a number of times. So you can say, since that I1, I2, and I3 is I in all cases, so you can say it's I plus I n times, and you can say n times I. So your H is given by n times I, and L is the mean length, which is again given by 2 pi r, and r being the mean radius. So this is the case of a coil where it has n number of turns. This was the case when you had only a conductor, only one conductor. So the difference is you have n number of turns in case of the coil. That's why H is n times. So H equals to Ni over 2 pi r, which does not depend on the material, only depends on the current and the configuration of the coil. So n a number of turns and the I. So it does not depend on the material. Only B equals to mu H. So B takes the impact of the type of the material through permeability. So that's about the Ampere's law application in order to develop an expression for B and H. Now let's consider how flux is related to these two quantities. Now flux, which was represented by phi, is the product of the flux density and the area of the surface or the cross-sectional area to which the flux density vector is perpendicular. So phi is given by B and A dot product. So here phi is the flux and its units is Webers. B is the flux density and its units are Weber per meter square. And A is the cross-sectional area and its units in standard units is meter square. Cross-section area in meter square. So now all three of them are related. How? So we have B equals to mu H, and H equals to, in case of a coil, okay, Ni over 2 pi r, and flux equals to B times A, and of course mu equals to mu 0 and mu r. So mu r. So mu r value will be given to us, and mu 0 value is known to us as 4 pi times 10 to the power negative 7. And units one more time. So B has the units of Weber per meter square. H has the units of amperes per meter. This is where it has come from. So we have H dot dl equals to I, or we also have H dot dl equals to Ni. So the units of the H are amperes, the right hand side, divided by meters, and in this case you can say the units of the H is ampere turns per meter, okay, and the units of the flux is Webers. Now let's take a look at an example. So this is an example where we need to calculate H, B, and phi for a coil that I'm gonna draw soon, and we need to use the mean value of the torus diameter as L. Assume that the torus is made of silicon iron. So this silicon iron will require us to know the flux density, okay, or relating H and B, or knowing the mu. Okay, so we have the example here. So we need to calculate H, B, and flux for the winding given to us, and we use the mean value of the torus diameter as L, and it's made from silicon iron. So what we need to do in this case is we need to calculate H, B, and phi. So let's look at what will be the steps which we will follow. So let's see how to calculate H. So H is given by, in this case, and it's the same exercise we did in order to develop the expression using Ampere's law. So H is going to be Ni divided by 2 pi r, and r we're going to say at the mean length or mean radius. So is N known to us? Yes, N is known to us as 200. Is current I known to us? Yes, it is 4.1 amperes. Is the mean radius known to us? So the mean radius will be here. Okay, this is where the mean radius will be. Okay, so this is where the mean radius will be. So we need to calculate the mean radius. Okay, so in order to calculate the mean radius, we're gonna say it is given by R1 plus R2 divided by 2. So R1 is 5 and R2 is 5.5 divided by 2. Or you can say that this is 5, that's 5.5. So this width is 0.5 and half of it is going to be 0.25. And the distance we require is 5.25 centimeters. So H will be N is 200 multiplied by 4.1 divided by 2 pi multiplied by 5.25, but since this is in centimeters, it is converted to meters. Everything has to be in standard units. And you get the value as 2492 in ampere turns per meter or amperes per meter. Okay, 2492. Now in order to have B, so B is going to be either mu H, or we can use the characteristic graph. We know that this is made from silicon iron. So for all ferromagnetic materials, we have graphs available, which is called BH saturation curve, which gives you a graph between B and H. So if we know one of them, we can, using the curve for the particular material, we can know the second one. So this is made from silicon iron. And I'll show you guys how the graph for this given to us looks like. We have, this is how the structure, the configuration of this core is on which this coil is wound. Okay, so what is the area? You can see that one dimension is 1 centimeter and the other dimension is 0.5. Okay, so area is given by 0.5 times 1. Okay, so area is, okay, so this is a graph between B and H. We calculated the value of the H as 2492. And here are the units, so ampere per meter or ampere turns per meter. So the closest one to 2492 is 2500, because from this graph we might not be able to locate 2492 point. So 2000, 3000, and this is 2500. And what are we using? We're using the silicon iron. So for silicon iron, this is where silicon iron is. This is the graph for the silicon iron. So on 2500, we go to the curve and we see what is the value of the B. So I'm going to say B equals to 1.6, and the units are Teslas. Okay, so if we know mu r, we might have used that method as well. In this case, we have used a graph for doing that. And then comes the flux phi. So flux phi is given by B times the area, and B we just calculated. Area is given by, so you can say, you can see in this case on the previous page, 0.5 times 1, and it's a centimeter square. which is 0.5 centimeter square. So flux is 1.6 times 0.5 times 10 to the power negative 4. And this gives you 0.8 times 10 to the power negative 4 in Webers. Or you can say it is also 0.08 milliwebers. All right, 0.08 milliwebers. So that's about magnetic fields. All right, so let's continue. So we're looking at the forces now. So one type of force, we have forces on the charges moving in a magnetic field. Forces on the charges moving in a magnetic field. So that's a force on an electrical charge Q, let's say, which is moving with velocity V through a magnetic field of strength B. So that force is given by force on a charge Q moving with velocity V inside a magnetic field of strength B. So that's the force given by. And the amplitude of this force is going to be given by QVB, sine of the theta, which is an angle between V and B, because it's a cross product. So let's say if you want to look at the direction, let's assume that this is the direction of the magnetic field, and this is the direction of the moving charge, and that's the angle between the two vectors. So your force will be here. So this force will be the charge Q, which is here actually. Okay, and Q V cross B. All right, and in this case the force is measured in newtons. Q is the charge in coulombs. V is the velocity at which the charge is moving in meters per second. And B is the magnetic field in Tesla. Second type of force you have is forces on current-carrying conductors. So those are the forces experienced by a current-carrying conductor placed in a magnetic field, and are electromagnetic force. And that's the basis for the operation of the motors, generators, or all electrical machines. The amplitude of the force depends on the orientation of the conductor with respect to the direction of the field. So we're looking at forces on current-carrying conductors. Let's say here you have magnetic field and the current carrying conductor inside the magnetic field. Let's say here you have a magnetic field from a permanent magnet, from an electromagnet, it could be from anywhere, but let's say this is how it looks like. And let's say this is the north side of a magnet, and on the other side you have south side of the magnet. So the magnetic field lines, there they are, and from north to south, so that's the direction of the magnetic field. And now let's place a conductor, a current-carrying conductor inside this magnetic field. Let's say this is the conductor placed inside this magnetic field. And of course we need to show that there's a current flow. So in order to show the current flow, we're going to connect this conductor to a battery, the two ends of the conductor. Okay, and that is making the current to flow in this direction, so leaving the positive side and entering the negative side. I and I. Now the force is greatest, so the force on this conductor, okay, is here. This force is the maximum when the conductor is perpendicular to the field, the way it is right now. When you change the direction of this conductor parallel to the magnetic field, so how it's going to be parallel to the magnetic field, so again, let's assume the magnet this way. That's a little bit easier to draw. Okay, and S. And again, the magnetic field lines. And now let's say the conductor is placed parallel to the magnetic field. Again, it could be a current carrying conductor. So this is the direction of the current. So force is maximum in this case. In this case, when conductor is perpendicular to the field, and force is 0 in this case when it's parallel to the field. Who? Conductor. So force is 0 when the conductor is parallel to the field. And the maximum force acting on the conductor is given by F equals to B L I, where F is the force on the conductor in newtons, B, as everybody knows, the magnetic field, which is produced by these two, or this magnetic pole pair right now, the north and south, so magnetic field. And magnetic field is measured in Tesla. L is the length of the conductor. So the inside in the magnetic field, whatever length is inside in the magnetic field, so that's the L. L is the length of the conductor. And the units will be meters. Conductor. Units will be meters. I is the current flowing through the conductor in amperes. All right, so it's maximum when it is perpendicular to the magnetic field lines. It is 0 when it's parallel to the magnetic field lines. Let's continue going, and I'll show you guys a generic case where you know, okay, this is the amplitude of the field and how you will know the direction of the force acting on a straight conductor. Now let's assume that here is the magnetic field present from a magnet. And the lines of field with the direction from north to south. And in this case, I'm going to use the third dimension in order to show the current flowing through the conductor rather than the second dimension. So let's say here is a conductor placed inside the magnetic field, and the current flowing through the conductor is labeled by a cross. And what does this cross mean? So that the current is flowing into the page, okay? So here it says current carrying conductor with current flowing into the page. Now, the blue lines you find, they are the magnetic field lines from the magnet. If you have a current carrying conductor, there will be a magnetic field from that current flow as well, which is called electromagnetics, right? And now this is a conductor, so you're going to use right hand rule with your thumb pointing in the direction of the current, which is into the page, and your fingers will curl in the direction of the magnetic field. So your fingers will curl with your thumb pointing into the page. Your fingers will curl clockwise. So this is how the direction of the magnetic field will be. Let's use green in order to show the magnetic field lines because of the current carrying conductor, because of the current flowing through the conductor. And the direction will be this, clockwise we said. Now what you observe, and this is clockwise, right? Same line. What you observe, you see the same direction for the top part between the blue lines and the green lines. You see the opposite direction for these lines between the blue and the green for the part which is below the conductor. And at the same time, we also know field lines never cross. Never cross. So what I have drawn is not good. So what will happen is the blue and the green lines will combine together. They will leave a greater intensity in the part above the conductor and lower intensity of the field below the conductor, because above the conductor they're in the same direction, below the conductor they're in the opposite direction. So in actual practice, practically this is what you're gonna see. Not the diagram one I have drawn above. So this is what will be actually present there. Let's say here is your conductor with current flowing into the page, and the field lines will now be. So the field lines will go like this. There will not be any crossing. Okay, this will be the actual magnetic field looking like. So what do you feel? What do you feel? That there is a force on this conductor downwards. Okay, there's a force felt on this conductor downwards because it's a stronger field in here and less stronger field at the bottom. So this will be the force experienced by this conductor. Okay, now this force is given by Fleming's left-hand rule. With the left-hand rule, so with your left hand now, left hand gives the direction of the field. Direction of the force. With your left hand, not right hand, left hand, with the first finger, with the second finger and the thumb all pointing, all at right angles to each other. The first finger is the direction of the magnetic field, and in this case it is towards right. The second finger is the direction of the current, which is into the page. And your thumb gives you the direction of the force, which you can see now pointing downwards. Okay, so that is how we know the force, and its amplitude is given by B L I, where B is the field, L is the length of the conductor in the magnetic field, I is the amount of the current. So we're clear about the direction and the amplitude of the force on a current carrying conductor inside the magnetic field. Okay, so now we're looking at the voltage induced in a conductor moving inside a magnetic field. So let's say it was the same current carrying conductor as we have seen the force on, and now let's say it's a moving conductor. Okay, let's assume that it's the same magnetic field with the magnetic field density B. It's the same conductor with a length L, but now let's say it is moving at a speed or at a velocity V in meter per second. So if that is the case existing, then we're going to have the voltage induced at the two ends of the conductor, and that voltage induced is given by BLV. That's the amplitude again. So induced voltage is E in here and is measured in volts, so the units are volts. B is again the magnetic field density, and the units are Tesla or Weber per meter square. L is the length of the conductor in meters, and V is the velocity in meter per second. So if you do not have a moving conductor, then the voltage will not be induced, or it requires something else. And this V here is the relative speed of the conductor. Now in this case, we're looking at the amplitude E equals to BLV, and the direction now, the polarity of this voltage will be defined by Fleming's right-hand rule. With the Fleming's right-hand rule, again, your first finger, second finger, and the thumb pointing at right angles to each other. So your first finger is the direction of the magnetic field. Thumb is the direction of the motion, velocity vector, and your second finger tells you the direction of the induced current or the polarity of the induced voltage. Okay, so that's all, and after this we're going to do magnetic circuits, so that we'll do later. Thank you.